Afaf, your mic is off.
Oh, yeah, sorry, sir. Yeah, the sixth one, only. 37 possesses 1 year.
Okay. So an ion with mass number 37. So A is equal to 37. Or rather, I think I should write it like this. We have some element X, 1 unit negative charge. It is having a negative charge. If the ion contains 11.1% more neutron than the electrons. Okay. Find the symbol of the ion. So number of neutrons is equal to it contains 11.1% more neutrons than the electron. Okay. So we have number of electrons, we have electrons plus we have 11%. 11.1 means 11.1 divided by 100 into the number of electrons. Correct? Yes or no? This is the meaning, right? Yes or no? Tell me.
Yes.
And then it is saying that it is having a negative charge also, 1 unit negative charge also. And if the ion contains, so we are talking about ions, right? And then it is saying will find the symbol of the ion. Mass number is equal to, so I can also write mass number is equal to number of neutrons plus number of protons. यहां तक क्या था आपने? हाँ या ना बताइए.
हाँ सर, यहाँ तक किया था मैंने.
उसके आगे आप अटक गए.
जी.
ऋषिता को करने दीजिए थोड़ा सा. Did you try this question, Rishita?
Sir, I couldn't get it.
Sorry.
Sir, मुझे नहीं आया.
अच्छा. No, I mean, you did not get the PDF or you did not get the question only?
Sir, I didn't get the question.
You did not get the question. Okay. So there are a few things that we can do here. First of all, can we start with number of electrons? Okay, let's say that. Let's suppose number of electrons is equal to X. Fine. In the ion, number of electrons is equal to X. And since we have an ion, the number of protons will be equal to X minus 1, because ion will have 1 extra electron. In neutral atom, what do we have? Number of proton is equal to number of electron. But since we have added an electron, the number of proton will be 1 less than the number of electrons. You got this? Yes or no? Tell me.
Yes, sir. Got it.
Okay. Now, similarly, I can say that number of neutrons will be equal to number of electrons is X plus 11.1 divided by 100 into X. Yes or no? Please tell me. Correct है? आया ना? बोलिए.
Yes.
Right ना? This one, the same thing. We have
Yes,
written
sir.
here. Okay. Can we solve this now? This will be equal to 100x plus 11.1x whole divided by 100. So this will become how much? 111.1x whole divided by 100. This will become equal to 1.111x number of neutrons. Correct? Yes or no? Tell me. Number of neutron is equal to 111. ये देख लीजिए. ये समझ में आया आपको? हाँ या ना? जल्दी पे आराम से देख सकते. जल्दी की बात नहीं, आराम से देखिए फिर बताइए. Understood this? You have taken the L scheme, we added it, then we divided this by 100. So we got 1.111x. Any problem?
No, sir.
No
No,
problem,
sir.
right?
No problem.
Okay. Fine. Now we are going to use this equation. Number of proton is how much? X minus 1. Number of neutron is equal to what? X minus 1 plus 1.111x This will be equal to how much? Mass number. What is the mass number? They have given 37. Now we got linear equation in how many variable? One variable. Linear equation in how many variables? One, na? Now we can solve this. We are going to separate the variables and the constant. So we have one constant here. That constant will go there. You will get x plus 1.111. X is equal to 37 plus 1. This will be equal to 2.111. X, which will be equal to 38. Right? Yes or no?
Yes.
Okay. Now, what will be the answer? Now, please remember, x will be equal to 38 divided by 38 divided by 2.111. Correct? Yes or no?
Yes, sir.
Can I write that it will be approximately equal to 17? Now, why I am writing 17 and not 16 point something? Because x is the number of what? Number of electrons. Now, when you have number of electrons, that number of electrons cannot be in decimal point. When you are going to ask, if someone is going to ask you, how many mango do we have in my house, in our house? And you come and you are going to say 5.732 mangoes. Then you will get a laugh on your face. And mangoes cannot be 5.732. If they're asking number, that means it is going to be a whole number. Apaf, Rishita, understood this or not? Tell me.
Yes, sir.
एक तो चीज हमने यहाँ पे बस गलती कर दी, इसको 19 लिखना था, 17 लिख दिया हमने. Oops, sorry. 38 divided by 2. अच्छा, divide कीजिए, कितना आ रहा है? You can use a calculator now. Tell me, Afaf, what this will be 19 by the way, not 17. My bad. It's going to be 19. 38 divided by 2.11, approximately 19. It will be 18 point something, right, Afaf?
Yes, 18.0009.
00. 18.0009.
हाँ, 000 आ रहा है. उसके बाद 9 आ रहा है.
Okay, fine. Then we are going to take 18 only.
Yes.
Okay, then we are going to take 18 only. So, no, what bad is very much. Okay, then we are going to take 18 only. Okay, so number of electron is equal to 18. Number of proton will be equal to 18 minus 1, that is equal to 17. So 17 means which element? Tell me. 17 is the atomic number of which element? Number of protons means atomic number. No? Arey, nahi yaad. Chlorine, na? 17 is chlorine, right? Yes or no?
Yes, chlorine.
So you can write the ion symbol as chlorine, 17, 37, and negative. Got it?
Yes, I got it.
So you please write this down.
Okay.
तो रिशिता, जब आपको नहीं आए ऐसे सवाल तो आप पूछिएगा ना.
हाँ, सर.
So Joel, we are going to start the discovery of fundamental particles. So basically we are in the topic of history of structure of atom. So discovery of electron, cathode, experiment, and those topics. Okay. So you are going to understand each and everything. कुछ भी relation पीछे के topic से नहीं है. This was the last lecture we did some electrons, protons, neutrons, and ये वही सारे सवाल हैं. From today's topic, you are not going to have any doubt. And then we have to see that how to cover the previous topics.
Done, sir. Clear.
Done. Now, write the topic discovery of fundamental particles. Discovery of fundamental particles. So what are the fundamental particles that we have? Electron, protons, and neutrons. are the fundamental particles. So first of all, the electron was discovered. So we'll start with the discovery of electron. But in order to understand the discovery of electron more effectively, we are going to look at an experiment. Now, where is the experiment? Experiment is not here. Just a second. I have to search it up now. Let me share my screen. Let me also share the audio.
Of electrons as particles. Next, we're going to look at the properties of electrons as particles and waves. This is called a cathode ray.
Is everything audible?
It generates.
Yes, sir.
Yes, sir, it is audible. Yes, sir.
Okay, Afa.
When they strike this white screen, you're going to see a green beam. And when they strike, this is called a cathode ray tube. It generates electrons, and when they strike this white screen, you're going to see a green
First
beam.
of all, can you see that? I mean, this part, as you see, just a second, if I can annotate anything, yeah. This part is transparent. This part is almost transparent, but this part is not very transparent. Can all of you see that? Joel, Afaf, and Rishita?
Yes, sir. I can
Yes.
see.
Yeah, okay, fine. So that white part is there, and that is a screen type of thing which is going to glow. Okay, when the electrons are going to pass, then that white part is going to glow. These parts are not going to glow. And it is made with zinc sulfide, and when zinc sulfide is hit with electrons, then only it can glow. So it is kind of a screen that you can say. Na? If you remember your 10th standard, so you had some screens in order to get the image from reflection or refraction chapter. Similar type of screen is there. Joel, you understood this? Yes or no? Tell me. Yeah, understood now? So voice is not very okay. Fine. Now let us continue.
Yes, sir. Can you hear me now?
Yeah, I can hear you.
Yes, sir.
Okay. So let us continue. Now, as you can see, these things are the cathode ray tube. I mean, this is the cathode ray tube. It has two ends, and inside this we have a gas, and then we have some metal plates. Okay. So when these gas are electrolyzed, that means you pass electricity, high voltage electricity, then what happens? There is a beam of electron. As you can see, the beam of electron is going from left to right side. Okay, I will stop speaking now. You listen to the audio in the video.
Prove that they're electrons by deflecting it with a magnet.
Okay, now what did they do here is that they put up a magnet here. So whenever there is an electron, whenever there is a charged particle in the presence of magnet, it is going to deflect. I mean, it is going to change its path. So as soon as they brought the magnet near it, then as you can see, the electrons are getting deflected, right? So it is
Yes.
obviously a charged particle, right? It is obviously a what? It is obviously a charged particle. Now, how did they say they are electrons? That means they are negatively charged particles, because they were coming from the negative end of the, whenever you have voltage, you have a plus sign and you have a minus sign. So these rays were coming from the minus sign and they were going towards the positive sign. So if it was a neutral speed, if it was neutral, then it would not have deflected from the magnetic waves. If it was positive, then it would have been repelled by the positive end. But what was happening, it was going from negative to positive. If it was automatically going from negative to positive, then obviously it will have a negative charge. That is why positive is attracting it, right? So that is why they called it electrons, and they are negatively charged because they are coming from negative side to the positive side. Actually.
This device also puts out X-rays, which I'm going to measure with
Now, this is another thing is that when you have high voltage and there is some electrons getting out, so electrons, they also emit some X-rays. Okay. Now they're having a Geiger counter with them. Now, what does Geiger counter do? It detects any electromagnetic radiations above certain level. So if you see the Geiger counter counting tick, 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 then that means there are some electromagnetic radiations. And I think they have set it for X-rays. That is why they are saying that it detects X-rays. So you will see some click, click, click in this type of sound. And as soon as they take it near to that electron beams, then that Geiger counter is clicking so fast that you cannot separate one click from the other also. Right? You can hear it once again. All right. Now, before they explain it, let me explain this. As you can you see a fan type of thing inside this spherical ball? Can you see a fan type of thing? Yeah. So this is a pinwheel. I mean, fan is nothing but a very sophisticated wheel. This is a similar thing. And the three blades that you can see, that those blades which are in kind of a weird direction. I mean, the fans generally, they are flat and they are having a horizontal surface, but it is having a vertical surface like this. Now, obviously, these are having some plates on it, right? Those plates are metal plates. When we are going to hit the metal plate with light, please remember, this is what I'm saying. When I am going to hit the metal plate with light, only light, then will it move? What do you guys think? अगर हम torch लेके आ जाएं, if I bring a torch and I glow the torch, then will the pinwheel move? What do you think? Will the fan move? If I bring a torch, can light make anything move? Afaf, Joel, and Rishita, tell me.
No, sir.
No, light cannot make anything move. And whatever property we saw earlier, that means with these electrons, what do you think? It is light only, correct? This looks like light. Yes or no?
Yes, sir.
Right. Now, then they did the second experiment and they were expecting that what we are going to expect now. Please remember how we do things in science is that we see some observation. So what did you observe here? That electron is light. You can see that, correct? Yes or no? You can see that, Hannah, Afaf, Joel, and Rishita. You can see that. Now, you said, okay, fine, electron is light. Then after that, you set up a next experiment and said that, okay, fine, if electron is light, then when I am doing the same experiment inside this spherical tube, the pinwheel should not move because electrons are light. And if I'm going to blow a torch, it is not going to move. So similarly, since electrons are also light, if I'm going to do the same experiment here, it is not going to move. But let us see what happens here.
Next, we're going to examine electrons as particles. This is a pinwheel device. Add a power source. The electrons strike the paddles, lighting them up and also making them spin. Let's see if this one puts out X-rays. Yes, okay. It does.
So this is how, now I hope you guys don't blame any scientists who first of all gave a theory, and then there were some other experiments which were done, and the previous theory was disproved, right? Because you just now saw that electrons are what? Electrons are light. But when you strike the spin wheel with the same thing, then what is going to happen? What is happening? The pinwheel is moving. So it can only move if the electrons are particle. Is that right? Yes or no? Afaf, Joel, and Rishita?
Yes, sir.
Hannah?
Yes.
So what happened? The light theory was just, but we also saw that electron is what? Electron is light. But it is behaving now as what? It is now behaving as what? As particle, because it is moving the pinwheel. And that is why electrons have dual nature. That means they can act as light as well as particles. Okay, so they have dual nature. They have light nature also. That is, light means wave nature, and particle means particle nature also. So the first experiment that we did, this is the experiment that we are going to learn in detail. That is known as the cathode ray experiment. And this was the discovery of electron. We are going to write a few points. All of you understood what happened? Yes or no? Please tell me. Anji, batai. All of you understood now what happened? Afaf, Joel, and Rishita.
Yes, sir. Yes.
Yes, sir.
Okay, fine. Now just let me bring up a cathode ray diagram so that you can copy it and I don't have to make it, right? Because exam वगैरह हमें तो नहीं देना है. You guys have to give the test and everything. So we are going to get a diagram. And the good thing about diagram is that it is representative. It is not actual photo. So whatever you saw, and this diagram represents it. And so it's good to have diagrams rather than actual photos, so that you can explain things. As you can see, everything here, don't start writing. Before that, we have to put up a topic, that is the discovery of electron and slash cathode ray experiment. What are we going to learn? The first topic, what was the pen that I used initially? The red pen, so I will use another pen. Discovery of electrons and cathode ray experiment. Cathode ray experiment. Now, first of all, as you can see what is happening, we have air at a very low pressure, and better word than air is going to be gas. So you are going to write gas rather than air. Okay. So what is happening? We have a gas, and gas is enclosed at low pressure, at very low pressure, and in a discharge tube. This is a tube, right? This is a discharge tube. So gas is enclosed in a discharge tube. Now this gas is then subjected to a high voltage. So we have a battery or something, and which is having a very high voltage, and this gas is then subjected to a very high voltage. Then there are some invisible rays which originate from the cathode towards the anode. When you are going to put up a screen like this, then only you are going to see, because as you can see in the experiment, as you saw in the experiment, certain portion of the cathode ray was not perforated. We call screen रखने को बोलते हैं perforated. Okay, so we did not have anything in this part, right? We don't have anything here, so we did not see any light here. But this part was complete. This was a kind of opaque thing, which was a screen, and here we saw what? Here we saw some greenish light. So obviously, electrons which we have, they are what? They are invisible rays. And invisible rays, these are originating from where? They are originating from the cathode and towards the anode, and they produce a greenish glow. They produce what? Greenish glow. And then what is going to happen if when they produce the greenish glow, when they are coated with, when the screen is coated with zinc sulfide, as I said, hai na? A screen which is known as zinc sulfide. So whatever is in the diagram and whatever we saw, we are going to write both of them concisely. So please start writing with me. When a gas is enclosed at very low pressure, and this pressure is almost 10 to the power minus 4 atm in discharge tube, and is subjected to high voltage, so high voltage, I mean, it is approximately 10,000 volts to high voltage. Then we see invisible rays invisible rays originate from the negative end. What is the negative end? Cathode. To anode. Anode is the positive end. Anode is the positive end, producing a greenish glow. Behind perforated anode. On the glass wall, which is coated with sulfide. Please make the diagram and write the screen. Let me know once you're done writing. Please let me know once you're done writing. Still writing. Apaf, Joel, and Rishita. Still writing.
Sir, I'm
Drawing.
Drawing. जल्दी से draw कीजिए. Scale. I mean, just make a rough drawing.
Then it's okay if we don't draw.
नहीं, draw it, draw it.
Okay.
Okay, draw it. Or what you can do is you can leave space so that you can draw later. But so it's a simple diagram, na? I mean, you just need to make two rectangles. One for the cathode, I mean, one for the discharge tube and one for the circuit. And you don't have anything else. You just need to, it's a simple thing. And then we have some lines only. Acha, if you are imagining why you have two vacuum pump, if you don't have a vacuum pump, then there will be a high pressure. Okay, So in vacuum, you don't have any pressure. So you can lower the pressure if there is a vacuum pump. Done writing? Yes or no? Tell me. बता दीजिएगा जब भी हो जाए. Okay, Afaf? Let me know once
Okay,
you're done.
sir.
Joel and Rishita are done.
Yes, sir, I'm done.
Yes.
Rishita, what about you? Done.
Oh, yes, sir.
Okay.
Done, sir.
Done. Very good. So, right, next. Characteristic of cathode. First point. They were called. Now, please write this with me, okay? They were called cathode ray because they originated from cathode. Next. They deflected. They got deflected. They got deflected in the presence of magnet. Meaning, cathode ray has charge. That point. Cathode ray travels from cathode, that is negative, to anode, that is positive, meaning cathode ray is negatively charged. With the next point. Cathode ray move pinwheel. Cathode ray move pinwheel if placed on their path. Therefore, cathode ray are particles. Next point. When they fall on heavy metal, they produce X-rays. They produce X-rays. Last one. Cathode ray travels in the speed of light. ठीक है? Is everyone done? Yes or no? Tell me. यहाँ तक लिखिए आप लोगों ने मेरे साथ साथ.
Yes, sir.
Yes, sir.
What
Done.
about Joel? Done?
Yes, sir. Yes, sir, I'm answering.
Okay. No need to explain any point, I hope. Is there any need to explain any point? No, right? Afaf and Rishita and Joel, tell me. No need to explain, na?
No, sir.
No, right?
No,
We have already discussed these things now. Next thing we have to understand. See, when you have charge and we are saying that it is a particle, you have charge and it is a particle. Please now keep your pens aside. Don't write anything and just listen to me. So they are saying that cathode ray, it has a charge and it is also a particle. Now, if it is a particle, that means it is going to have mass. It is going to have mass. Is that right? Yes or no? Please tell me. Correct?
Yes, sir. Correct.
Okay. Now, the next experiment that they did was, as you remember, if you read the first line, when a gas is enclosed at a very low pressure, what we say? When a gas, now we can have multiple gases in it. So they started experimenting with different gases and they compared their charge by mass ratio. Now, how do you compare charge and how do you compare mass? I will give you a very simple idea about it. If you have a high charge, that means when magnet is around you, then that particles are going to deflect more. Correct, guys? Yes or no? Tell me. And a charge may, whatever the variation in charge is there, you
Yes,
can
sir.
understand it by deflecting, by the deflection it shows in the presence of a magnet. Right? If you have very low charge, then it is not going to affect the deflection also, right? Something like that you can see. I mean, the deflection, the amount of deflection, it can be measured and it can be dependent on charge. And then the number of rotations of pinwheel, the number of rotations of pinwheel will be somewhat related to the mass, correct? Magnet. And this can be dependent on rotations of pinwheel. Right? So if we have a very high mass, then what is going to happen? If we have a very high mass, then there will be more number of rotations. Correct, guys? Yes or no? Tell me. Apav, Joel, and Rishita. Right?
Yes, sir.
Yes, sir.
Anna? Fine. Now they started experimenting with different gases, H2, N2, helium, O2. Fine. Now all of these different gases, they have different masses. They have different masses. Okay. But what they saw was, no matter what type of gas they are using, the charge by mass ratio, was always same. It was always same. Now this was an observation. Charge by mass ratio is always same. Now the conclusion from there, we can say that all of these emit same type of cathode rays. That means the negatively charged particle that is present in each and every atom is independent of the type of gas. It does not depend that negatively charged particle. अब तो हम लोग जानते हैं ये चीज, तो ये चीज बहुत आप लोगों को आसान लग रही होगी ये कहना अगर कहें. If I say something like that no matter if you take electron from hydrogen, helium, lithium, oxygen, or any other gas or something, that electron, if you take an electron from hydrogen and if you take an electron from helium, both of those electrons are identical. All of you know this, right? Afaf and Joel and Rishita. Correct?
Yes.
But now you understand how the experiments they can conclude this. Because we are getting same charge by mass ratio, that means we can conclude all the different gases, they are emitting same type of cathode rays. That means same type of negatively charged particle, and that negatively charged particle was called electron. Understood? Yes or no? Tell me.
Yes.
Apaf,
Yes.
Joel, what about you? Understood?
Yes, sir.
Fine. So I can write one more point. Charge by mass ratio. आखिर अभी आ रहे हैं. Oh my God! इतने दिन बाद अभी इतना लेट. Charge by mass ratio of cathode rays was found to be independent of the gas used in discharge tube. Assalamu alaikum, Akib. How are you? Akib Ahmed, how are you? Why are you so late and why were you absent? I am good, alhamdulillah. Why are you so late and why were you absent all of these days? Yes, Akib. Very fine. So, and why are you okay? Fine. What I mean, this answer is for today or what? Why were you absent then? Last class you did not, you were not present in the last class. Why was that? Daily आइए आप लोग समझे? Okay, Akib. For other classes, what other classes? Daily आइए. If you are not attending the class, then please make sure that you are watching the recorded lectures. Okay. Okay. Now one more thing. Okay, fine. One more thing is that आज की क्लास में आप बैठिए बस. एक तो इतना लेट आए आप, ठीक है? कुछ समझ में आना थोड़ा मुश्किल है ना? We have been telling a story. आप स्टोरी के बीच में आ गए, ठीक है? So you just listen and try to grasp how much whatever you can. Now Rishita, Joel, and Afaf. Okay, fine. That is good if you are able to understand. It's very nice. Now, so J.J. Thompson was the one who was doing these experiments. These experiment, cathode ray experiment, it was done by J.J. Thompson. Okay. And when J.J. Thompson saw that charge by mass ratio is same, that means we have a particle. Okay, fine. That's good. We have a particle which is there in each and every element. And that particle is negatively charged. And that particle can be taken out from the atom. We had the idea that there is an atom, but people did not know, like, inside the atom what things are there or how the things are composed inside an atom. People did not know. Now from this experiment he understood that, okay, fine, there is a negatively charged particle which is present inside the atom. From this experiment we can at least conclude that, yes or no? Tell me.
Yes, sir.
I mean, the electrons are present. How they are present, I don't know. How they are present, I don't know. We just know that electrons are present inside the atom. Now, if the electrons are present, which is negatively charged, there must be protons also. I mean, not protons. Wait a second. अभी electron proton हम लोग नहीं बोलेंगे ना. Electron proton हमको क्या पता? हम तो J.J. Thomson 1800s. I don't know electron. I don't know proton. So negatively charged and positively charged. Okay. So there are some negatively charged particles which are inside the atom, and these negatively charged particles can be taken out. Right? That is why these were ejected from the cathode. So they can be taken out. That means there are some entities, like they are fixed inside the atom. They are fixed inside the atom, which can be taken out. Is this concept clear? Yes or no? Afaf, Akib, and Joel, and Rishita. Correct? Hai?
Yes, sir, it is clear.
Fine.
Yes.
Now, if there are negative charges, to balance them, there should be positive charge also. There should be a positive charge also, correct?
Yes.
So J.J. Thomson tried many things to get the positively charged particles also. He did many experiments within this cathode ray, I mean within this discharge tube only, but he was not able to get anything from the anode side. I mean, if there is some positively charged particle, so that positively charged particle should come from the anode and it should go towards the cathode. But that wasn't happening. So he concluded that, okay, the complete atom is positively charged. What he said, the complete atom, because he tried so much, he did not get any particle. He thought that, okay, fine, maybe the complete atom itself is a positively charged thing. And inside them, we have negatively charged particles which are embedded. So he said the complete atom is positively charged. The complete atom is what? The complete atom is positively charged. This is a sign of positive charge. Right? Should I bold this? Maybe I should. Is it that? Complete atom is of positive charge, and the electrons, these are embedded inside the atom. Understood? Yes or no? Please tell me. How J.J. Thomson concluded this?
Yes, I understand.
Yes, sir.
Right. So you will write, by above observations. Joel, you understood?
Yes, sir. Yes, sir.
J.J. Thomson suggested the following. He suggested that atoms are positively charged. Atoms are positively charged. Said that it is spheres. Sphere with negatively charged electrons in it. Okay. This model of atom is AKA. What is the meaning of AKA? What is the meaning of AKA? You guys don't know?
Also known as.
Also known as. AKA means also known as. Please write this down. Let me know once you're done.
None, sir.
Now we have done discovery of
Cathode.
electron. Discovery of electron. Now the discovery of protons and discovery of neutrons are very small topics in the sense that we don't have to go into detail for them. Okay. So what pen I did use was so write the second. Discovery of protons. Now this was discovered by Goldstein. From observations of anode ray experiment. Now, Goldstein was one who was successful in doing anode ray experiment. That is why he suggested that there are some positively charged species also inside the atom. And then the same things was done, whether it is a wave or whether it is particle, and what is the charge by mass ratio. So charge by mass ratio is written by E by M. E divided by M. E means elementary charge and mass M means mass. Okay. So please listen, E by M of anode rays was found to be lesser than that of cathode. That of cathode rays. CR is cathode rays. What does it mean? Meaning, now, if the charge by mass ratio is less, that means this anode ray must have high mass. This anode ray must have high mass. That is why the ratio is less. Meaning, mass of anode rays was much higher than the mass of cathode rays. That is why you all know that mass of proton is very, very high. Mass of proton is very, very, very high than the mass of electron. Next point, again, they used different gases, and they found that charge by mass ratio was dependent on the type of gas they are using. So E by M of anode rays was found to be E by M of anode rays was found to be dependent on the gas used. Okay, then next point. E by M of hydrogen gas was found to be maximum. Meaning, hydrogen is lightest gas. Okay, then writing is not only almost similar things as that of cathode rays. It's just that some observations were different. All of you done? Afaf, Akib, Joel, and Rishita. Not done.
Done, sir.
Done, na? Okay. I hope the points are self-explanatory. If you want me to explain any one of the points, please let me know. Afaf, Rishita, Joel, Akib.
Sure, points are clear.
Points are clear. Okay, fine. Joel, everything clear, right?
Yes, sir.
Let us do the third, that is the discovery of neutrons. Now, right here, discovered by, do you know the name? Chadwick. Important point to note down is that the discovery of neutron was quite late. It was around late 1920s and all. The reason is that neutrons, these are not charged species. So it was very difficult to detect neutrons because they were not charged, they were neutrons. Okay. So please write, this was very late. As neutrons are not charged particles, and it was difficult to detect them. Okay. For neutrons, you have to just understand. I mean, we are talking about discovery only, right? Yeah. This was very late. I mean, this was discovered by Chadwick. The next sentence, this was very late as the neutrons. We're talking about discovery only. Yes. The same thing. Okay. Is everyone done?
Yes, sir. Done.
Okay, fine. So fine. Discovery of different subatomic particles is done. Now we are going to look at the models of atom, of which we have already seen one. Right, next. Models of atom. So we have already seen the number one model, that is Thomson model. Now we have written everything about Thomson model. We will just write down some limitations or drawbacks. I think drawbacks is a better word. Drawbacks. So the first drawback is that it is a static model and it does not talk about the seeds. First thing is that जब Thomson model आया, when Thomson proposed the Thomson model, he did not propose it with the drawbacks and the limitations, right? I hope you understand that. Afaf, Akif, Joel, and Rishita. When we write the drawbacks, when we write the limitations of anything, then we are talking in the terms of future. So what we know now, in terms of that, we will judge the Thomson model. So right now, we know that electrons move, right? We know that electrons move, but Thomson did not say anything about the movement of electrons, right? So we are talking from the terms in the perspective of future. We are in the future, and then we are judging the Thomson model. But at that time, when Thomson proposed this model, this was the only model which was available. There were no drawbacks, no limitation of the model which Thomson had. Okay. And similarly, the model of atom that we know right now, I mean, that is just a model of atom. It is not, we have never seen, we cannot see actual atom. That is why we make models of different things, right? Now, we really don't know what atom is right now. In reality, how would we know? We cannot see these atoms. There are some effects that we see on doing few things on atoms. And from those effects, there are some observations. And from those observations, we are going to say that, okay, fine, atom is like this, atom is like that. But after 100 years, maybe our assumption or our idea of atom becomes wrong. There are some other experiments, or when the machinery gets a bit more advanced, then we can do some more experiments, some higher level experiment, and then we can know a few new things about the atoms also. Nobody knows. So right now, our atoms model, it does not have any limitations, right? Because we are not in future, but maybe in the future it will have some limitations when new observations and new characteristics of the atoms have been found out. So please understand, as a, I mean, generally this is a notion. अच्छा, जब गलत ही था मॉडल तो पढ़ाया क्यों? अरे मॉडल नहीं पढ़ाया जा रहा है आप लोग. Please understand that also. बहुत सारे बच्चे कहते हैं ना, if something is wrong, why you are teaching this? Have you heard this? Yes or no? Afaf, Akib, Joel, and Rishita. सुना है आपने? नहीं सुना? सुना भी नहीं? आप नहीं सुने? हमारे बच्चे सुना है ना कि गलत था जब तो पढ़ाया क्यों? So the reason is we are not teaching you these Thompson models. We are the essential idea of NCERT and CBSE is to teach you observations and conclusions. As we saw na cathode ray, they were called cathode ray because scientific methodology, because they originated from cathode. So now you have an idea how to name things. In further life, if you are going to get some variable, something, then you have an idea how to name things. They got deflected in the presence of magnetic field. This is an observation. Now what we can conclude from here, meaning cathode ray has charge. Cathode ray travels from negative to positive, meaning they are negatively charged because positive is attracting them. Okay, so from how do we get conclusions? How do we get, I mean, also think about this, Okay. Atom. Can you see an atom? No, I cannot see an atom. But can you say that atom के अंदर electron होता है, उस पे negative charge होता है? Can you understand what type of magic is this? I can't even see what is behind my wall, which I cannot see. But with experiments, I can tell what is the charge of an electron. Okay, so this is the scientific methodology that NCERT and CBSE have. That is the reason they have put this thing. Okay, it's not that you have to learn Thomson model. It's not that you have to learn about the Rutherford model. It is to bring up some scientific idea. Okay, you have to have a scientific mind. That is the reason these things are present. Okay, so please इनको उस तरह please don't take in the perspective कि ये model पढ़ना है. मैंने model नहीं पढ़ना है. आपको पढ़ना हुआ क्या था, वहां से लोगों ने किया क्या. Okay, so I mean, each and everything is done by imitations only. Those of you who know how to cook something, you have imitated someone, and that person has imitated someone, and only after many imitations you can, if someone is there, if there is a cook, if there is a chef, that chef must be the chef must be a student of another chef, right? But after a long, very long time, when someone is student, he's just copying the chef, the head chef, they are just copying the head chef. So now he knows thousands of different dishes and he has copied it from his master. After thousands of dishes, after copying thousands of dishes, he can take one ingredient from the 1,000 dishes, and then he can come up with a new dish of his own, right? So anything new, anything creative can only be done after a large number of imitations, right? For example, how am I teaching? I have been taught by many teachers from my 11th standard, 12th standard, then I did my BSc, then I did my MSc, right? Now I have taken good parts from all the teachers, what I learned, and then I'm bringing, now my way of teaching is very different from all the other teachers. That is only after thousands of hours that I have spent as a student, then next 1,000 of hours that I have spent as a teacher, right? So similarly, scientific mind can be born only and only if you start imitating others who have passed the experiments that have been done. You imitate those experiments, and after that only you can bring some new experiments. That is the reason. The reason नहीं है कि आपको Thomson model याद करना या Rutherford model याद करना. My voice is lagging. Is my voice lagging for everyone?
No, sir.
अच्छा, थैंक यू. अदरवाइज मेरा पूरा लेक्चर खत्म कर दे. इतना अच्छा हमने तकलीफ किया है ना, वो खत्म ही हो गया. चलिए. Now Thomson model drawbacks from our perspective. Thomson को तो ही ना पता. Thomson तो बहुत खुश, उसको लगा हम क्या मॉडल बना के गए. So the limitations that we can see now is that, please write, it is a static model. And does not talk about the motion of electron in an atom. Second, it does not talk about stability of atom. Does not talk about stability of atom. Write this down. Let me know once you're done.
Done, sir.
Done, sir.
Next is Rutherford's model. Now, obviously, we are going to see the experiment. Then only we are going to talk about the model. Okay. Sorry. Wait a second. Can you see the screen? Can you hear the voice?
Yes, sir.
Yes, sir.
Let me increase the quality. Now, just one thing is that this is a modern reconstruction of the same experiment. Okay. So I will let you know, or maybe inside the video also, they are going to let you know what Rutherford used and what they are using. Okay. So it is not as Rutherford did the experiment. It is few modification has been done. Okay. But those are not very, very large modification. It is quite near, at least in principle, it is very near to the Rutherford's estimate. Let's go.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it.
They're
Now,
talking about the which model? Tell me. This is the Thomson model, which is saw, right?
Yes,
Correct. Sorry. You can hear things properly, right? I don't have. Is my voice necessary to explain things, or can you understand each and every word they are saying? My interruptions, are these interruptions necessary? No or yes? Tell me one thing. Afaf, Rishita. Are they necessary? Not necessary?
sir. Anything is fine.
Hormones.
Yes, Rishita, complete your sentence.
Sir, anything is fine.
Anything is fine. Fine. So you watch the lecture. Watch this whole thing.
Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the center of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it'll just and it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, and what we're doing here, is taking a beam of particles, firing it at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference.
Okay, fine. So I think I need to explain a few points here, right?
Yes, sir.
Tell me. Okay, fine. So let me bring up a picture that is going to help. Okay, for model. So Rutherford, so alpha rays is something that he hit on gold foil. So gold, you almost know. Alpha ray, you can just understand what Rutherford understood. He knew that alpha ray, these are highly positively charged particles. They are positively charged particles. Okay, highly positively charged particles. They are heavy and they are positively charged particles. Fine. So Rutherford only knew that much about it, that those are positively charged heavy particles. Now, the experiment that he did, I hope you can see that here. Fine. Now see here. So first of all, you are going to look at this box. So this box, it contains a radioactive source. Now that radioactive source is going to it is going to emit. Emit is the word. It is going to emit alpha particles. Okay. Now, obviously, it is going to emit the alpha particles in each and every direction. It's not going to emit the alpha ray particles in only one direction. It's going to it's going to emit in each and every direction. Okay. Now, so we are going to put this in a box and we are going to cover it up in all the directions except one, and we are going to put up a hole here. So this lead shield, it is protecting the alpha ray particles from coming behind. So those alpha ray particles cannot come behind. It can only go through a small section which is here. Now again, they have put a lead screen. This lead screen is again protecting the light, protecting the alpha rays which are coming like this, and like this. And here we have again a slit. Slit means there is a small hole. There is a small hole here. Now the alpha particles can only move from this hole and this way. Now they hit the gold foil. Fine. Now we are not going to say first of all what happened, but what are we expecting when we hit the gold foil? So what are we expecting is accordance to the plum pudding model that we already had. This is the plum pudding model, right? Yes or no? So this is the model of atom that we already have. Now, if you are going to put, when we say alpha ray particles, then those alpha ray particles are what? Those alpha ray particles are what? Positively charged. Now, when we have positively charged something and it is going to strike, what happened here? Those alpha ray particles, if they are going to strike a negatively charged, here you have negative charges and the complete atom is positively charged. Complete atom is what? It is positively charged. So what do you think what is going to happen? These rays are positively charged. And here you have positive charge once again. So what should happen? Tell me. Positive will repel each other, right? Yes or no? Correct?
Yes, it will repel.
It will repel each other. And if I am going to put up a detector here, then I should not detect any alpha rays, that is the positively charged rays. When I say alpha, you should remember that those are positively charged rays, right? Because whatever model of atom that we have right now, the Thomson model, that should be deflected by the positive atom. The positive atom should deflect it back. That means we should not get anything in this particular. When I'm going to put it behind the alpha, behind the gold foil, then we should not get any detection of alpha rays, correct? But what actually happened was, most of the alpha rays, they just passed through the gold foil and they struck on the surface which was just behind the gold foil. Most of them, almost all of them, what they did, they passed through the gold foil and they struck on the, and then they struck on the screen which was just behind the gold foil. Okay, fine. Then that was a bit amazing. So they said, okay, fine. I mean, not all rays, but most of the rays are getting onto the screen that is behind the gold foil. So let us now move the screen from A to B. Now they saw that, okay, fine, we are getting some hits, but the number of hits that we are getting in the B position is very less than the number of hits that we were getting on the A position. Then they, now still, if you look at the B position, that B position is still behind the gold foil. Can you see that, yes or no? Right?
Yes.
Not exactly behind, but I'm saying it is not in front. For example,
Lightly
C is
behind.
in front of the gold foil. C comes before the gold foil, right? Above.
Yes.
Okay. Apap, can you say something? I just need to check my mic and headphones. Apap, can you say something?
What should I say?
That's it. Fine. I just wanted to check my headphones whether they are working or not. Okay.
Oh,
Fine. So the number of hits that we got on A was the most. Then the number of hits was in B, and then we got very less number of hits when we put the screen on the C position. That means there were a few observations. What were the observations? We can say that with each observation there will be a conclusion. With each observation there will be a conclusion. Observations क्या थे? Most of alpha rays passed through gold foil without any deflection. Without any deflection, meaning most of the atom is vacant space. Some alpha rays got deflected. From their path. Meaning atoms have positively charged. That is why they are getting deflected positively charged heavy nucleus. Positively charged heavy nucleus, because alpha ray was also very heavy, and if it is deflecting the alpha ray, that means the nucleus should also be heavy, and it should also contain positive charge because it is repelling that alpha rays which are positively charged. Then last point, some of the very, I should say very few. Very few alpha rays bounced back. Meaning, nucleus of atom is very dense. ठीक है, तो देखिए हर पॉइंट से, that means when this first line that we wrote was the observation from the A position in the experiment, this A position. Then the second line we wrote was the observation from the B position, and the last line that we wrote was the observation from the C position. Okay, now please understand that when I say the last point, now you will say that, okay sir, what is the difference between the first second point and the last point? Second point is saying that it is having heavy nucleus. Heavy means what? It is just heavy. It is not telling you anything about the size. Okay, it is not telling you anything about the size. Heavy cheese बहुत बड़ा भी हो सकता है, बहुत छोटी भी हो सकती है. Last point is that very few alpha rays bounced back. अगर बहुत कम alpha ray they were coming back, that means जो directly hit कर रहा है nucleus को, the number of alpha rays that is hitting the nucleus is very less. That is only possible if the nucleus is very small, and a very small thing with a very high mass, that means it will be very dense. All of you understood this lesson, or please tell me? Small size, very dense, and small size we declare, and very small size, very small in size. All of you understood the three positions and the three observations that we got from them and the three conclusions that we wrote from them. Yes or no? Please tell me.
Yes,
Yes.
understood.
तो
सर इस
आज की
डायग्राम को ड्रॉ करना है.
नहीं ड्रॉ मत कीजिए डायग्राम को, है ना. डायग्राम को आप ये वाले डायग्राम को तो मत ही ड्रॉ कीजिए. इफ यू वांट टू ड्रॉ डायग्राम देन आई विल गिव यू अ डायग्राम व्हिच इज थोड़ा सस्ता वाला, है ना. थोड़ा सस्ता डायग्राम ले लीजिए, आप उसको ड्रॉ कर लीजिएगा. ठीक है. I mean the ABC point was actually very good here. That is why I chose this for explanation. And for the, wait a second, have you wrote this down?
Yes sir.
Yes, sir. Written.
Fine. So आप इसको बना सकते हैं, इसको बना लीजिए. Just these lines are important. Okay, as you can see, most of the lines are here, है ना. A few lines are deflected, that but it is still in front of the in front of the, I mean in front in the sense they are after the gold file, and very less, that means only one ray is behind the alpha ray. ठीक है, चलिए. I mean it was, as they said, it was a very dark room and they have to take this screen. This is a stripe, right? So I think, I don't know whether Rutherford was there in the experiment room or not, or his PhD students were doing these experiments. Getting confused. Either it was the X-ray that was done by Roentgen, or this was Rutherford. I don't remember. But just imagine they are having alpha rays just behind the gold file. Then they are slowly moving, and then they have to observe that when the alpha ray is hitting the screen, I mean that screen lights up for a second. So you have to observe that also. Okay, fine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it is lightening up too many times when the screen is just behind the gold file. Then they moved a bit, no hit. Then they moved, okay, one hit. Then they stayed there. Fine. Then that means they stayed there, and then they counted. Okay, fine. After every 20 seconds, there is a hit. Then they moved again. Then they moved again. Then they moved again, and so on. They calculated each and